So today we are going to see one of the very important ideas which most of you have encountered in your college days, which is why we multiply matrix the way it is. Why not we can do exactly same thing as we did for addition, which is term by term addition. So let's say when we have defined addition, we took the first element from the matrix and the corresponding element from other matrix. We add them up and we get the answers too. Similarly, we take 2 plus 0 and so on and so forth. Now the question is, why not we can't do it for multiplication? Why not I am multiplying 1 into 1 to get 1, 2 into 0 to get 0, 2 into 2 to get 4, and 3 into 1 to get 3. Or maybe can I define it in some matrix world? Will it be useful? So let's motivate ourselves with one of the very easy to understand idea. And here we go. As we know, the matrix algebra is very strongly based on solving linear equations. Hence, it has derived its name as linear algebra. So let's consider some variables x1, x2, which is related to other world variable y1, y2. Let's say we have another relation z1 and z2. So this behaves like a parameter to connect x1 with z1, right? So there will be some relation between world 1, world 2, world 2, world 3, and hence x world and z world will also be related. So now you can relate them in any way. You can relate y1, y2 in terms of x1, x2 using some quadratic expression, cubic expression, sinusoidal way, maybe logarithmic way. But what I'll be doing right now is a very simplistic case, which is using linear expression. We'll try to read y1 and y2. So let's, for the sake of understanding, let's take y1 is related with x1 and x2 as x1 plus 2x2. Of course, you are free to put any value of x1 and x2 as the coefficient. And y2 is linearly related, let's say something 2x1 plus 3x2. So given a value of x1, y1, x1, x2. So given a value of x1, x2, we can find y1 and y2. Let's say we have another relation. To be specific, let's say we have linear relation between z1 and y1 as well. So let's say z1 equals y1 and z2 equals 2y1 plus y2. Yes, you're completely free to put z1 equals 3y1 plus 7y2 or 2024 y2, whatever you want. I'm just taking a simplest example to understand the physics more than the mechanics, right? Okay, so now a very simple question. We know y1 is related with x and the z are related with y. So can we relate z with x? Of course, yes. So let's start eliminating. So z1 can be written as simply x1 plus 2x2 and z2 is 2y1, which goes to x1 plus 2x2 plus y2 2x1 plus 3x2, which amounts to 4x1 plus 7x2. Okay, so far so good. So let me write this information in a cool way, in a nice fashion. Let's try to put this information. So clearly y1, y2 we can write just as a coefficient. So because the coefficient of x1 and x2 we can visualize, so just a cool way of representing this information can be, we have 1, 2 and 2, 3. So it's nothing is great. Okay, just we're trying to represent in this cool fashion so that it looks nice. Let's represent z and y relation exactly in the same way. So we have z1, z2, y1 and y2, and that was y1 coefficient was 1. There was no y2 here because I can write it 1 y1 plus 0 y2, right? Other was 2 and 1. So again it can be expressed in this fashion. So these numbers basically signifies how x and y are related, right? So basically y1 related with 1x1 and 2x2 is just a way of writing the above expression, and z1 is related with this. And then we have seen like we can even express the relation between z and x directly. So z1, z2 and x1, x2. So this was working as a mediator, right? It was acting as a mediator. And we got very nice answer 1, 2, and we have 4, 7. Okay, so far so. If you see the structure of how we produce 2 is basically from 2x1 plus 2x2, right? Similarly 2 into 2 plus 3. So this was coming out of 2 plus 2 and this was coming out of 2 into 2 plus 3. So let's keep it in mind. Maybe it can give some magical awakening. Okay, this feels quite unrelated. If we try to express this information in a very systematic way, so let's keep x1, x2 over here and y1, y2 over here. So basically I've rotated this entire system, right? So if you just take it up and rotate it, so in front of x1, 1 and 2, 1 and 2 should come. So let's write 1, 2, x2, 2 and 3 should come. So it will give 2, 3. Similarly, if I take, because I've written x1, x2 over here and y1, y2 over here. y1, y2 was the mediator, so let's keep y1, y2 over here. And z1, z2 top. By doing so, this is acting as a mediator. So it's basically we are trying to get a relation between x1, x2 and z1, z2. It's just an artful way of placing the structure. Okay, so that we can easily keep track of this. So z1, z2, front of z1 we have 1, 0. So again it feels like we are rotated. And z2 is 2, 1. Right? And that should be related with, let's keep, since we have got these two guys same, so we want to keep x1 vertically and z horizontally, right? So x1, x2 to preserve that mathematical structure horizontally, and finally z1, z2 vertically. So again this will be rotated. So in front of x1 we are having 1, 4, so that will come over here. Front of x2 column is 2, 7, so that will come over here. Now I can give this a treatment of matrix. So I can, because that's just a symbol, it looks nice to define symbol like this. Now can you see any correlation? Like it's basically relation between x1 and z1 is the eliminant of y1. Fundamentally we are eliminating y1, y2 from the system. Okay, elimination of y1, y2 from this relation is directly connecting z with x1 and x2. So that is basically captured in a nice way via these two coefficients. And this is the answer for eliminant. Answer for eliminant. Now you can clearly see the cos of 4 was 2 plus 2. The cos of 7 came from 2 into 2 plus 3. So 3 you can write it as 3 into 1, right? Something. So 2 into 2 plus 3 into 1, that gave 7. Right? Okay. 4 came for 2 plus 2. So basically 4 origin was 2 plus 2. So that can be written as a 1 into 2 plus 2 into 1. We want to see the pattern, like trying to find the rule of the game, or 2 into 1 plus 1 into 2 kind of a structure. 7 came from 2 into 2 plus 3. So either I can write 3 into 1 or 1 into 3 by the commutative property. And that gives some magic, because we can clearly see to produce 7 we need 2, 3 and 2, 1 kind of a structure. So 2, 3 is already available, because 7 is something which gives you a greater hint of it, and 2, 1 is already available in this column, right? So fundamentally this represents the y value, right? So this represents the connection between y1, y2 with x1, x2. This represents connection of y1, y2 with z1, z2. So when we are multiplying, basically we are connecting x1, x2 with z1, z2. So you can clearly see how to get 7. It's 2 into 2 plus 3 into 1, because that's how it came. And now I'm tempted to think for 4, which is 2 into 1 plus 2 into 1. So is 1 to 2 1 available in the picture? Yes, it makes sense because we have already 2, so that demanded 2 and 1 demanded 1. So we have got 1 2 and 2 1, right? So now we'll think of from where 4 came. So it's like 2 1 1 2. So 1 2 into 2 1, that gave birth to 4. And that makes your logic so simple, because if I take the first row, multiply by this column term by term. So I'm taking 1 2 multiplying with 1 0 to produce the first term of this entry. When I multiply this, the rule of the game now, which we feel is imitating, first guy is multiplied with first, second guy is multiplied with second. So it's kind of dot product. So 1 into 1 plus 2 into 0. Similarly, this guy when multiplied with the second one, so 1 into 2 plus 2 into 1 gives 4. 2 into 3 into 1 to 0 gives 2, and 2 3 to 1 gives 7. So I hope you have understood this. Basically, multiplication amounts to simulation and mimicking the idea of solving linear equations. So this was whole about why we are tempted to multiply exactly the way we are doing so. So it's just reincarnation of the steps of solving linear system of equations. Now, why practically it is of any use? Because maybe you could have just defined this. So it can be equally a good definition. In fact, it's a more easy definition. So is it practical to define matrix the way we have defined? So let's see one of the motivational example to support this idea. Try to understand this with a motivational example, and we'll decode the exactly same problem in different ways. So we have got a matrix 1 2 2 3, another matrix 1 2 0 1, and now we know by the multiplication we are getting result 1 4 2 7. Okay, so we'll try to decode this problem in a slightly different way. We'll analyze this problem from a different perspective. Let's say 1 2 2 3 represents AB and CD collection. We have C, D, E, F. So we'll try to decode the problem in a different way. Let's say I associate CT name A, B, C, D, and E, F to the following matrix. What does it mean? Hold on. So we have CT AB, CD, and EF. Now I want to count. Okay, so with this motivational example, we'll try to decode this multiplication in a slightly different way from data science perspective. Let's say I associate arbitrary the CTs A, B, C, D, and EF. What does it mean? So number of flights which are available from city A to C is 1. Number of flights available from E to D is 2. Number of ways or flights in which you can go from B to C is 2. And number of ways to go from B to D is 3. So now this data set, this matrix, this numbers collection represent the number of ways of going from a particular destination to the other destination. Let's do it by visually, and let's connect number of ways of going from A to C. So we have one connection. From A to D we have 2, B to C we got 2, B to D we have 3. Now let's try C to D to EF. So from CD to EF, C to E1, we can repeat the same thing. Let's use a different color. C to F, we have 2 ways of going. D to E, we have no way. And D to F, 1 way. Now interestingly, let's count the number of ways in which you can go from directly A to E. So from A to E, we have only 1 way, right? And which is clearly represented over here, because this is as if you are directly going from AB to destination EF. Interestingly, let's do from A to F. So from A to F, we have two ways till D, and then one way. So in this path, we'll have two ways, plus you can go via C as well. So we have two ways over here because this is unique path, so two ways. That gives four ways, which matches with the idea. Let's go from B to E. So from B to E, we have two ways, and that's it. And the last one, B to F. So we have three ways over here. Is there any way to go from B to F? Yeah, clearly. So we have three ways over here, two ways to go to C, and then other two ways to go to F. So that will count to 2 into 2, which is 4. Because for every way, let's say if I take this path, I can have two available flights. Similarly, for this path, we'll have two available flights. So basic principal counting tells you 4 plus 3, which gives you 7. So you can clearly see if we have 2 cross 2 matrix, what hidden information it has. And fundamentally it's doing exactly same thing, because we are relating x1 x2 with y1 y2 and y1 y2 z1 z2. So this linear relation is basically counting number of connections between the source point and a destination point, which is fundamentally fabricated and installed in the process of solving equation. Very interestingly, if we'll have now some 3 by 3 matrix, let's say 10 11 12 13 14 15 and 16 17 18, you know we'll get this answer. And now you can come with 3 city ABC and then DEF IJK and start drawing all the connection. So we have A B C D F. From DEF we need to go to IJK. So of course DEF is a mediated city, so we'll have again connection between ABC and DF. So you can start with, let's say, one connection with D to I. We'll have 10 connections, 4 5 6 7 8 9 10, and like this. If we'll draw all this directly, we can count number of connections from A to I without basically counting it. So I hope that motivates you, and clearly you can extend this idea for n cross